Hello, welcome back. 2330 Introduction to Organic Chemistry. We're going to start with Chapter 8 today. And so I'm going to do something a little different. You'll notice that I did get to grade the exams and post those exams this morning or this afternoon. So you should be able to see those. Those are the curved grades based on the raw scores. But don't worry, you'll notice that we have a lot more of the class activities and homework, the lower stress versions of the class that take up a lot of the points. So there are still, plenty of time to increase your grade and do homework and do the activity. So don't worry about that. Just keep going ahead and let's just trudge on with the next chapter. So for this week, we're going to do chapters 8 and 10. The reason I do them together because they have a unique property that all of them have a hydrogen bonded to an atom that's other than carbon. And because of that, we have some special properties associated with that, including hydrogen bonding or the ability to hydrogen bond or not hydrogen bond. So I'm going to combine both of those together. And so those are going to be alcohols, thiols, and amines in particular. And then there's another version of the thing called ethers that we'll talk about today. So the full videos for these chapters are up on YouTube. They're on the Introduction to Organic Chemistry playlist. And so I actually included that in the email today. So if you want additional, that's the full slides. I'll actually be presenting full slides on these two chapters because of the, the complexity of that. But there are the other chapters, on Top Hat, there's the goals chapters. So the goals chapters are still there. You can still review them, but we're going to do the full slides for class today. So we have chapter 8's homework will be due on Friday at midnight this Friday. And then chapter 10 homework will be due the following Wednesday, because we're actually not going to get to chapter 10 until Wednesday today. Okay, so are there any questions about administration at this point? Okay, so coming up on the schedule is for this week, we're going to be doing chapters 8 and 10, and then we're going to be doing chapter 9. Chapter 9 is all about benzene. We got to learn some stuff about resonance and new nomenclature. So I like to, pull 8 and 10 together because they're very similar, and then have a separate time set aside for chapter 9. If we have time, I want to have an activity with chapter 9, and it's about naming the aromatic compounds. However, if we don't, it's not on the schedule, but it'll give us an extra grade in our activities section there. Okay, without further ado, let me go ahead and share my screen. And chapter 8. Again, if you have questions, the chat room's open, or you can unmute and we can talk. I'm going to go ahead and put my cascade view up over here. So you should be seeing my slides now. This is chapter 8, alcohols, ethers, and thiols. And so we're going to go over what those different groups are. We know how to name them now, and so I'll kind of hit some highlights about naming. But then I'll show you the structural differences and some of the actual property differences. And the property differences come from how they are bonded, okay? So if we move on to section 1, alcohols are a class of organic compounds that have the OH functionality. That OH functionality is usually called hydroxyl, and it's almost always bonded to an sp3 hybridized carbon. Now, the reason is we have a special compound where it's bonded to an sp2 carbon, but it actually goes back and forth with another compound. We'll talk about that in another chapter. So we're looking for specifically hydroxyl attached to an sp3 hybridized carbon. Okay, and so this is the alcohol group. And so what's interesting to note is that our carbon is also tetrahedral. So it's got 109.5 degrees, or at least tries to. And the oxygen actually has that same sp3 hybridization, but 2 of those positions are taken up by lone pairs. That's why the oxygen and hydrogen in alcohol are always looking at that bent configuration, just like water, because there's 2 lone pair clouds taking up the other portion of space, giving us that tetrahedral electronic structure and that bent molecular structure. Okay. So when we name these right here, so everything we named up to now were alkanes. And so they had that E at the end. That suffix E indicates there's nothing else but carbon-hydrogen bonds. Okay. And if you had a double bond, it's ene. And if you had a triple bond, it's ine. But that last E signified you had no other functional group. So now we have another functional group. Okay. And that functional group is the alcohol. And so we call it the all at the end of it. So basically, we would take our longest chain. So if we had a pentane, and then we hooked a pentane, and we hooked an alcohol onto it, we would have to drop the E, pentane, and add the OL, pentanol. So it becomes pentanol. Okay, and so that's the way to do it by a U packing name. And you try to, because you've changed the name, you try to give that alcohol the lowest number possible. If it's at the end of the chain, it's assumed to be 1, but all other times you have to do either a 2 in front to signify where the alcohol is, or an N-2-all. And that'll signify exactly where that alcohol is. Both names should be acceptable. Now, that's the IUPAC name, but these are so common that we actually have some common names associated with them. And what you would do is you would just add the alkyl group. Let's say you had the hexane with an alcohol on it. You would call it hexyl because it's an alkyl group. So it'd be hexyl alcohol, and there'd be 2 words. So that's how you can tell the difference between the IUPAC name and the common name. Is the common names typically are 2 words. The IUPAC names are strung together in a single word with dashes and commas, etc. Okay, so here's some examples of that. A nice small one with 2 carbons, that's an ethyl or an eth for your IUPAC. And then we drop the E and add OL. And so we have ethanol right here. But its common name is based on the fact that we have the ethyl group here. And so it'd be ethyl alcohol. So when we look at some of those common names for structures, we also have this little group here, this Y group here, which we call the isopropyl group. And so when we make an alcohol out of that, we call it isopropyl alcohol. However, in the IUPAC system, we have 1, 2, 3. That alcohol has to be on that number 2 carbon. And we denote that with the 2-propanol. Notice it's in the front for this one, but sometimes you will see it, a N-2-OL. So, but for the most part, you'll see it written like this. Then as things get more complicated, you would just use their simple names. So the longest chain here is 3, so that'd be prop. So it'd be propanol, but then we have to denote that there's a substituent here. And because the alcohol is here, we want to give the alcohol the number 1 position. That's making our methyl at the 2 position, giving us 2-methyl 1-propanol. Now that group here that, if I circle the group in red, this group itself has a special common name of isobutyl. And so you can also call it isobutyl alcohol. Okay, so it's fairly simple. You just got to remember, drop the E, add the OL, and make sure that if it's not at the end of the chain, like in 1-butanol here, you signify where it is. Now, whenever you have a functional group on a ring, okay, and it's the highest priority one, that begins, where'd it go? Oh no, okay, there it is. The rings always, when you name the ring for the functional group, you have to always look at it as position number 1. Okay, so let's go ahead and do a quick naming of these different things right here. So we have, let's see, there's 6 carbons, 7 carbons, 8 carbons, and it has the alcohol at the end of the chain. So we can just call that hexanol. No, there's 8 carbons, sorry. Octanol. Octanol. And if you want to be precise, put 1 octanol. Okay, so this has 1, 2, 3, 4, 5. So we have pentanol. Okay, but the oxygen is on the 2 position, and 1, 2, 3, 4. If we named it the other way, it'd be in the 4 position, and we don't want to do that. So we would have 4-methyl 2-pentanol, okay? And then if we had a much longer chain like this here, we have two groups of 3 carbons each hooked to 1 carbon and then a CH2. So let's redraw that so that we can see that. We have an OH, and then we have 1, 2, 3, 1, 2, 3. So that's what these two groups are here with that CH2 there and that. So this is going to give us 1, 2, 3, 4, 5 as our longest chain. So it'd be pentanol, and then it'd be 1, 2, 3. So it'd be 2 propyl, because it's a substituent and it's got 3 carbons on it, dash 1 pentanol. And if we were to name this, we would name this the cyclohexanol, and we'd have a 2-methyl because this is going to be our 1 position because we're naming it for that. Okay, so the naming is actually fairly straightforward. And then as you get to what we call higher priority groups, groups that make the alcohol no longer named for it, for example, if it was a carboxylic acid or a ketone, then it becomes a substituent. And as a substituent, it's called the hydroxide. So if it was on the 2 position, you'd call it 2-hydroxy, and then the rest of the name. Okay, so now you can name it as the parent, changing the name of the compound, or as a substituent. Okay, so when we have more than one alcohol on the same compound, and it still changes the name, we include the di, tri, or tetra in front of the alcohol to tell how many OHs we have. So in the case of this simple one right here, ethylene glycol, oops, there we go. Ethylene glycol right here, we only have 2 carbons, so that's the ethyl group, okay? So we keep the E at this point and call it ethane diol, okay? Now, the common name for this is ethylene glycol, and you might know this as antifreeze for your car. Really toxic to cats, don't give it to cats. And so you have one of the hydroxides on the 1 carbon and one on the 2 carbon, so it's going to be 1,2-ethane diol. Okay. Now, if we extend that chain, we still have to show where they are. So in this case, this would be propane diol, and we have them in the positions of 1 and 2. We could also have another isomer. If we put it over here, it would be the 1,3-propane diol. And then if we have 3 like this is propane triol. It's also known as glycerin or glycerol. It's a very high boiling material that is edible and acts to wet things like your skin. Okay, so now that's great, and that's simple because you're naming the end of the chain. However, we got to remember that's your suffix. That's the last part of your name. We still have to think about the infix. So if you have an alkane and no other double bonds, then you can just name it the way we did, where we have the AN, drop the E, and add OL. However, if you have a double bond or a triple bond, you have to include that in your infix. This is still, so this is still your prefix. Right here, the hexa, still your prefix. The ene is your infix, and the all is your suffix. Prefix, infix, suffix. So when we add that there, it changes a little bit and turns it into hex. And then we have to make sure we have the ene on it. And then wherever the alcohol is, we have that 1-all. So it's hexene 1-all. Okay, and this is what we call the ene-all rule, because you have an alkene and an alcohol in the same compound. Okay, so in this case here, we have 2 groups opposite each other, so we can call that the trans or the E. And we have a total of 6 carbons for our prefix. We have a double bond for our infix, and we have an alcohol naming our parent chain. So that's the enol rule. And if you had an alkyne here, you would do hexyne 1-ol as well. Okay, so now let's talk about the physical properties and why these are a little bit different. When we were talking about just the hydrocarbons, okay, all they had were those induced dipole, or London forces or dispersion forces. Very weak force. The only thing that was changing the boiling point of our compounds were basically adding more carbons or making them more spherical. So if they were more spherical, they had a lower boiling point. But if they were longer, they had more of those van der Waals forces and it would come up. That changes once we have alcohols. Okay. Now, the reason this changes is because we have polar bonds, so we have a dipole moment, but we also have a hydrogen that can hydrogen bond. And remember, we have van der Waals forces, dipole, and then hydrogen bonding is even stronger than that. So let's look at how that looks in our system here. So if we looked at bond polarity, if we just looked at the electronegativity, these two, there are a couple apart on the table, and we know that there's a difference. So that there's going to be a polarity of the oxygen is more electronegative than carbon, and therefore it's going to pull more electron density toward it. Okay. And if we looked at the electrophilicity of oxygen and hydrogen, we'll see that oxygen is more electrophilic than hydrogen. So guess what? It's also pulling it in that direction as well. So that means the oxygen is partially negative and the carbon and the hydrogen are partially positive. So that means that we have a polar molecule where we have a zone of negative charge and then a zone of slightly positive charge. And that gives us this permanent dipole, and that it can be used for bonding to other molecules. So because of this, we also have that hydrogen oxygen, okay? And that hydrogen oxygen bond is a very polar bond, and that hydrogen can easily be bonded partially to other things because it's partially positive. So if you can imagine, it's trying to be attracted to a partially negative part of another compound, and that's what we call hydrogen bonding. It's this attractive force between that partially positive hydrogen and a partially negative oxygen or nitrogen or fluorine, okay? So what we see with this is that hydrogen bonding is actually fairly significant. It's 2 to 5 kcals per mole, and it's much weaker than a covalent bond, but it's stronger than a dipole interaction. Okay? So that means that the hydrogen bonding is going to have a significant impact on the physical properties, specifically melting point and boiling point. Okay, so what do we mean by hydrogen bonding? So the idea is that if you have a partially positive hydrogen on one molecule, and it starts floating by another molecule that has a partially negative section on it, it's going to be attracted to it electrostatically. And because it's not a full bond, it's not really there, it's just an association, what we have is that you can have multiple hydrogens attracted to different partially negative parts of other molecules, okay? So in this case here, we have two molecules that are hydrogen bonding through their hydrogens to the same oxygen here, right here. But then we also have that hydrogen on that oxygen, hydrogen bonding to another molecule. Now, the number of hydrogen bonds you can have to any electronegative atom all depends on sterics, how big the groups are around it. So if you have something big and fluffy like a T-butyl group, it's going to be hard to do hydrogen bonding. But if you have something small like ethanol or methanol, it's going to do a lot of hydrogen bonding. And if you think about water, it doesn't even have those carbon groups in the way. It can hydrogen bond on both sides of it. So it definitely affects the physical properties significantly. Okay, so one of the things that we can use this for is that this intramolecular hydrogen bonding. So in addition to intermolecular, which is between two different molecules, we can also have intramolecular hydrogen bonding. And what intramolecular hydrogen bonding will do is it actually makes things easier to dissolve or dissociate into other systems. Okay? So while this is a very complex system, it actually has a couple of the functional groups that we're going to talk about today, including the alcohol group. This is chapter 10, the amine group, and this is an ether group right here. So we're going to be talking about all of those different functional groups in these next two chapters. Okay, so how many hydroxyls are present and how can we classify them as primary, secondary, and tertiary? Okay, just like when we had carbons, where you had one carbon attached to a carbon, that made it a primary carbon. Two carbons attached to a carbon made it a secondary carbon, and three carbons attached to a carbon makes it a tertiary carbon. We use that same nomenclature with how many carbons are attached to the carbon we have the oxygen on. Okay, so in this case here, we have this hydroxide, this alcohol here, and it's bonded to two different carbons. So we call that a secondary alcohol. Okay, so in that case, we have a secondary alcohol there, and we have a secondary alcohol here, and we have a secondary alcohol here, and we have a secondary alcohol here. So a primary alcohol would look something like that. A secondary alcohol is going to look something like that, and a tertiary alcohol is going to look something like that.
Professor Urban, wouldn't that alcohol with the methyl group hanging off in the center, wouldn't that be a tertiary alcohol?
Yes, it is. Thank you.
Sorry.
So we have a secondary, a secondary, a secondary over here, and that's an ether, and that's a tertiary right there, and that's a tertiary right there. So, and the real important part about those primary, secondary, and tertiary alcohols is they react slightly differently and they have different hydrogen bonding. We'll see that when we look at their boiling points and melting point changes. So the other question is, how many amine groups are present and can we classify those? Now, amines are a little different. Amines are classified by how many carbons are bonded to them. Okay, so in this case, we only have one that I see. I think we have that one there. Let's see, I don't see any other ones. And this happens to have 1, 2, 3 carbons bonded to it, so that makes it a tertiary amine. We'll go into that in more detail in chapter 10. Let's see. Of the 4 hydroxyl groups, some of them can be involved in intramolecular hydrogen bonding. Okay, so let's look at that. So let's use a different color here so we can look at the hydrogen bonding stuff. This hydroxyl can be hydrogen bonding to this group and that group there. This can be bonding to the nitrogen there. Let's see. This one can hydrogen bond to this group over here. So you can see that there's a lot of opportunities for bonding just within a molecule. And then once we put it in a solvent, it typically bonds to those solvents as well. Okay. So we'll start to look for these different similarities in the structures that we see. Okay. So lots of places for the intramolecular hydrogen bonding. And in most of these cases, we're making a 5 or 6 membered ring when we do this, by the way. And we'll look at that in a different chapter as well. Okay, now let's look at just the effect of that hydroxyl and what that hydroxyl does for solubility and for boiling point. Now, remember, our solubility has to do with that alcohol being able to hydrogen bond, and our boiling point is also going to be affected by that. So let's look at the similarities between it and see what we see. So when we compare these right here, what we're doing is we're trying to get things approximately the same molecular weight. The first driving force for any boiling point and melting point is molecular weight. As molecular weight goes up, the boiling point, melting point will go down within that same class. But we've done something different now. We have an alkane, which cannot hydrogen bond, only has van der Waals forces. And now we've changed it so we have a hydroxyl that can hydrogen bond. And so the first thing we see is that the boiling point jumps by over 100 and not 150, about 80 degrees Celsius, okay? And the other thing that happens is it becomes soluble in water. It's infinitely soluble in water, meaning that you can do 0% methanol to 100% methanol and every mixture in between. So just adding that OH now makes it water soluble and jumps the boiling point by 80 degrees. So let's see how that affects it when we move up a carbon. So if we go from propane to ethanol, we have about the same molecular weight again. And we have a significant change in boiling point, a little over 100. And we also are still soluble in water when we have the alcohol in it, but insoluble in water when we don't. Okay, great. That means anything with a hydroxide must be infinitely dissolvable in water, right? Maybe not. Let's take a look. All right, so if we go up one more carbon here, we have butane and propanol here. Our boiling points are about 100 degrees apart. It is still soluble in water, and this is still insoluble in water. So maybe that rule's gonna be right. All right, let's go up one more carbon right here. And what we see is our boiling point is still about 100 degrees difference, but look, we're losing solubility. There must be a reason we're losing solubility. Okay, if the hydroxide is the only part that's hydrogen bonding, and that's the part that's pulling it into solution, that means there's a limit to how many carbons it can pull into solution with it. So let's look at this. So in this one, we had 1 carbon, 2 carbons, 3 carbons, and now 4 carbons. At 4 carbons, we're not entirely infinitely soluble. We are not infinitely soluble, meaning that the carbon section is starting to resist or overpower that ability to hydrogen bond. Okay, and therefore we're losing solubility. It still helps the boiling point, but we're now losing solubility in water. And when we go up one more carbon, it even gets worse. So it looks like one OH can pull in approximately 5 carbons to make it slightly water soluble. If you go up to hexanol, it stops being soluble. And so that is the rule, is approximately 1 hydroxide per 5 carbons, and you can have it be partially soluble in water. Now, what does that mean if we have 2? Okay, here butanol was barely soluble. Let me actually change colors. Butanol here was barely soluble in water. However, we add another OH to it. Now we have 2 OHs for 4 carbons. And guess what? It's completely soluble in water. Okay, so the general rule is about 1 hydroxide per 5 carbons, and it will be partially water soluble. And that has everything to do with the hydrogen bonding. Okay, so interestingly enough, we did acids and bases, right? And most of the time we think about water as being neutral, right? Well, we have to also think of it as being a Lewis acid or Lewis base because it has a lone pair. If it has a lone pair, then it can interact with a hydrogen, an acidic hydrogen, to become the conjugate base. Okay, I'm sorry, the conjugate acid. So water can act as a Lewis acid or as a Lewis base in the system. Okay. Now in this case here, if we look at the pKa of, in this case, ethanol, which is about 15.5, and water, which is about 15.7, we see that that's a very, very small difference. Okay, very small difference, meaning that in aqueous solutions of alcohols, you have the same pH as water because they're both trying to act as acids and they're both trying to act as bases. Okay, so that's one of those interesting things about the alcohols. So the alcohols are about as acidic as water. So if we put that on a pKa scale, now let's start with our strong acids, which of course are less than 0. Then our acetic acid right here, pKa of around 4. And then we look at methanol. Methanol, water, and ethanol are all right about the same. Okay. However, as you go from these primary alcohols to a secondary alcohol to a tertiary alcohol, the pKa goes up. They are less acidic the more bulky the system gets. So primary alcohols are more acidic than secondary alcohols, and secondary alcohols are more acidic than tertiary alcohols. All right, so like I said, water can act as a Lewis acid or base. Well, alcohols can too, okay? Because they have those Lewis dot, that lone pair right here and here, it can act as a Lewis base. So just like before, we have to compare the pKa to the acid to the pKa of the conjugate acid to see which way the equilibrium lies, okay? And therefore, most alcohols can function as weak acids and weak bases. So if you have a strong protonating agent, they will become protonated, and you will have the protonated alcohol as one of your species in solution. Okay, so this is a reason why we kind of stress the Lewis acid base theory, because when you have these lone pairs, you now have a Lewis acid. When you have a hydrogen hooked to a heteroatom, you have an acid. So it can act as a base or an acid. So you have to think about which way it can be used. And because it's in the middle, it can be used as both. All right, now, that being said, we can do some really cool things with alcohols, okay? Alcohols will react with lithium metal, sodium metal, and potassium metal, and several other active metals. And what they do is they actually oxidize the metal, which is the metal which is in oxidation state 0. It's actually stealing electrons away from it and turning that metal into a positively charged species, and taking the hydrogen on there and adding an electron to it. And when you get 2 electrons that are added to hydrogens that have 1 electron on them each, they combine to form diatomic hydrogen. So let's look at that in a little more detail here. So in this case here, when we have 2 equivalents of alcohol and 2 equivalents of sodium, we're going to take 1 electron from the sodium and give it to this hydrogen. We're going to take another electron from the second one and give it to a second hydrogen. And we'll end up with hydrogen gas. And we'll have 2 equivalents of the salt of the alcohol. Now we call those alkoxides, or alcohols that have been made into salts. So they're alkoxides. And in this case, we made it out of methanol. So it's sodium methoxide. Okay. Now, remember, our alcohols were not very strong acids. Okay. However, not strong acids turn into strong bases, right? So alkoxides are actually stronger bases than the OH here because of that association between not being very strong. It's slightly weaker acid than water. That makes it a stronger base than hydroxide, the conjugate base of water. So that being said, our alkoxide also has a negative charge on it. And our negative charge can be used as a nucleophile in nucleophilic substitution reactions. So remember when we did SN1, SN2, we had to say whether it was a good nucleophile or whether it was a base. And then we had steric base and not steric base. Well, methanol, methoxide right here, is one of those strong bases that's not sterically hindered. So that means you have to look for your beta elimination reactions or your E2 reactions. All right, so how can we use this to our advantage? Well, what we can do is that alcohol, we can use it as an alcohol and do some other things to it. However, under acidic conditions, we can protonate that alcohol and make it a good leaving group. And so what we can do is in a strong acid, we can actually displace the OH and put a halogen there, okay? Now this works extremely well with tertiary alcohols, okay? And it typically is water soluble because you have your acid most of the time in an aqueous solution. So concentrated HCl plus a tertiary alcohol will give you your tertiary alkyl halide. Cool thing about that is this is no longer soluble in water and it separates out or boils off so that you can, can isolate it easily. Now, Primary and secondaries don't react under these conditions. And the reason is because we cannot form the carbocation. This involves the formation of a carbocation first, and then the chloride coming in as our weak nucleophile. Okay, so that being said, that means our small primary and secondary alcohols don't do this. Even though they are water soluble, they will not do this because they cannot form that carbocation. Okay, so what if you have a water insoluble alcohol? How can you get it to go? Well, the cool way to do it is that HCl is a lot of times you find in an aqueous solution with water, but you can also make it as a gas, and you can bubble that gas through a different solvent as long as that solvent is polar, like diethyl ether or THF. You can dissolve and dissociate that acid and it'll do the same reaction. Okay. So under those conditions, we can actually use the primary and secondary alcohols under this same condition will work because in this case, we have the iodines and bromines act as strong nucleophiles. Again, this is insoluble. This is not in water. It can substitute to give us our alkyl halides in a non-aqueous solution with concentrated HBr and HR. And there's another way to do this too. Okay, no, we're going to talk about this. Okay. So here's the mechanism on why we can do that with the tertiary alcohols. And it has everything to do with forming that carbocation. Okay. So the first step in that is we actually protonate the alcohol. Okay, that's a common one of our 5 things that we can do in the mechanism. And so we protonate the alcohol and it gives us this group right here. Okay, hydroxide is a really bad leaving group by itself. But now that we have this, when it leaves as water, which is a neutral molecule, which makes it a good leaving group. Okay, so now that we have a good leaving group that leaves as a neutral species, and we have water, which is a polar protic solvent, which supports carbocations, we can form this tertiary carbocation as our intermediate, and then wait around for chloride to react with water to give us our chloride ion, and then go ahead and interact with the carbocation. So this is why that solution-based, that water-based system works only for tertiary alcohols, because we form that carbocation. Okay, so if we try to do that same reaction with the alcohols in water, it doesn't work very well because we cannot form the carbocation. We'd be forming a secondary or a primary carbocation, and therefore that part doesn't work. Okay. So what we have to do is instead do it in a non-aqueous solvent because we're not using the carbocation, and we have a much higher concentration of nucleophile. So that's why we have concentrated bromine. So we have a lot of the nucleophiles around to kick off our neutral molecule in an SN2 type reaction. Okay, so we protonate, wait for the nucleophile to displace the water. Okay, so, and this is true for most reactions. Most reactions are governed by electronics or sterics. Okay, so in the case of tertiary alcohols, we almost always form our carbocations. Okay, carbocation right here. In the case of our primary alcohols, we never form a carbocation. We always do SN2 reactions, never SN1. Okay, now 2s can go either way. If they're sterically hindered, it might go form the carbocation. If it's not sterically hindered, it will go SN1. So in the case of having something like a straight chain secondary alcohol, it's going to be an SN2 reaction. But if you had a secondary alcohol that had 2 long chains like this, and this would be more likely to form your carbocation and give your SN1 type product. Okay? So we can combine all of our SN1, SN2 stuff to look at sterics and know which mechanism we can use. Okay, so if it's really hard to do that primary alcohol, because you have to use it in concentrated solutions and you can't form that primary carbocation, we have a special reagent we use that makes it much, much easier, okay? And it's called thionyl chloride right here. So it's SOCl2, and it looks something like ClCl right here. And what this does is this actually reacts with the alcohol first to form a better leaving group. And then when it does that, it can have the chloride come and displace the better leaving group and turn it into the primary alkyl halide. Do I have that? No, I don't. But anyway, so the concept is that you would react your primary alcohol with thionyl chloride, and then it's going to give off byproducts. One of the byproducts is HCl, which is the hydrogen, and one of the chlorines are going away as that. You have the SO right here. That's where the oxygen of the alcohol is going to give us SO2. So this chlorine's taken away in that, this is taken away in that, leaving just the chlorine left. That chlorine is transferred to the alkyl chain. Okay. And so this is a really special reaction. We use it a lot for two different reactions, specifically primary alkyl halides, specifically alkyl chlorides, and we'll use it again when we talk about carboxylic acids. All right. So the other thing we can do with alcohols is, depending on whether it's primary, secondary, or tertiary, we can do a beta elimination. Okay, this is supposed to be beta elimination right here, where we're going to pull off a hydrogen, one carbon over, and the OH to give away water. So that's why we call it dehydration. We're going to remove water and create a double bond. Okay, so when we have primary alcohols, this is really high temperature and a catalyst. Okay, and if you think about it, you have to be able to protonate the material and then have something come along and tug on that beta hydrogen first, because you can't form the carbocation. So it takes a lot of heat. Okay, so secondary alcohols, because a secondary carbocation is not that bad, it'll undergo this at a slightly lower temperature. And tertiary alcohols, because they can form carbocations, that'll actually happen at room temperature. So notice that the temperature goes up as the ability to form a carbocation goes down. Okay, so let me show you some examples of that right here. So if we just had ethanol right here, so we have two carbons and an alcohol, ethanol, we have to heat that to 180 degrees, probably under pressure, and it's going to create a double bond between our two carbons, which is this right here, plus water. That's why I call it dehydration. Water is always one of the products of the reaction. Okay, so in the case of cyclohexanol, this is now a secondary alcohol. In our secondary alcohol, it doesn't take as much heat, but it does form our double bond and give away water. Dehydration. Now, if we have our T-butanol here, or our methylpropanol here, it actually just heated a little above room temperature and boom, it breaks down into this methylpropene, also known as isobutylene, but again, it liberates water. Okay, so dehydration of alcohols gives us a double bond and water. Okay, moving right along. Okay, now, there's a problem once you get into having alcohols in the middle of your system. Which double bond is going to form? Okay, so for example, here we have a choice. We have our OH here, but remember, this is a beta elimination reaction, meaning that we have a hydrogen here that's a beta hydrogen. We also have a hydrogen here that's a beta hydrogen. Okay, so which one will it choose? Okay, so if we did this side with the beta hydrogen, we'd end up with the alkene on the end of the chain. If we did it on this side here, we'd end up with the alkene in the middle. So the rule is, the more substituted double bond, the more stable. So if we redrew this as that versus that, this double bond has two substituents, therefore it is favored over this double bond, which only has one substituent other than hydrogen. And if we look at the product ratio here, we see that it is tilted that way. We have 80% of it being that one. And if you look at statistics, there's only 2 hydrogens here to pull away, and there's 3 hydrogens here to pull away. You'd think it'd be the other way around. But it's all about the stability of the double bond form. The more substituted double bond, the more stable the compound, and the more likely it is the primary product of the reaction. Okay, so let's look at the mechanism a little bit. So the first step of our mechanism is always in acid catalyzed system, is always add a proton. So we're going to add that proton and create this really good leaving group now, this oxonium ion. Okay, so it's alcohol that has a proton on it. Now it's positively charged, and it can leave as neutral water. So step 2 is that we'll probably break that bond and liberate this as our neutral species and give us our secondary carbocation. Okay, so now we have a couple choices here. The next thing that has to happen is we have to have something, and in this case water, is going to act as a base and pull off the beta hydrogen here or the beta hydrogen here. Okay. And if we pull the beta hydrogen off from this side here, it'll give us the more substitute product, and therefore it's going to be the major product. Okay. So in a primary alcohol, it's a little different. We have to go through an E2 mechanism because we can't form that primary carbocation. So in that case, what we see is first is, of course, protonation to give us our good leaving group, but we can't form that carbocation. So we have to wait around for our water to pull on one of the hydrogens that's on that beta position, that one over from the alcohol, to give us our double bond and give us water. And notice we've regenerated our acid that we can use back in the beginning. So in this case, we have a 2-step or an E1 reaction versus the E2 reaction. In the E2 reaction, you form, this is an E2 reaction because you have 2 molecules together at the same time during the elimination. So this is our E2 and does not form that carbocation. All right, so if we can take away water to form an alkene, that means we can take an alkene and add water to it. And so when we do that, we can actually convert back and forth between the alkene and the alcohol just by using an acid catalyst. Now, the way to drive it one way or the other is the more water you use, the more likely it's to be shifted to the alcohol side. If you're removing water as you go, it's more likely to shift it to the alkene side. Okay, so you can direct the reaction by just adding or subtracting water. If you add water, it goes to the alcohol. If you take away water, it goes to the alkene. Okay. So we can do a couple things with alcohols. We can convert them to alkyl halides. So that's one reaction we want to write down. We can eliminate water, and that's another reaction we want to write down. And that's going to form alkenes, and it'll always try to form the more substitute alkene. Okay. The next thing we can do is with primary and secondary alcohols, we can oxidize them. What we mean by that is we can take away hydrogens. Oxidation is the removing of 2 or more hydrogens or the addition of oxygen. Okay? So in the case of the oxidation of an alcohol, we are going to remove 2 hydrogens. All right. So in the case of a primary alcohol, we're actually going to end up with an aldehyde. So we have H and our, whatever our R group is here, okay? And we can do this using a specialized reagent. Now, if we have a secondary alcohol right here, and we remove 2 hydrogens, we have a hydrogen here and a hydrogen there, we end up with a ketone. Removing 2 hydrogens gives us that ketone. So they both give us carbonyls. They both removed 2 hydrogens, but it gives us 2 different functional groups. Primary alcohol give an aldehyde. Now, if you don't control the reaction, that aldehyde can then oxidize off this hydrogen and turn into a carboxylic acid. So we have to be careful about which reagent we use. Okay, so let's talk about primary alcohols first. If we use a strong oxidizing agent, this is called chromium oxide or chromic acid, right here, H2CrO4, right here. If we use chromic acid on a primary alcohol, the first thing that's going to happen is it's actually going to make that aldehyde. Unfortunately, that aldehyde is also easily oxidized. And basically the only thing you'll isolate is the carboxylic acid. It's going to oxidize once and then then add an oxygen to it and oxidize it again. Remember, oxidation is removal of 2 hydrogen or the addition of oxygen. Okay. So using chromic acid, we can actually convert any secondary alcohol to a ketone because it stops at the ketone. Okay. So what if we want to stop at the aldehyde? Okay. To stop at the aldehyde, we have to decrease the oxidation strength of our oxidizer. And so we use what we call PCC, pyridinium chlorochromate. So instead of having our chromic acid right here with 4 oxygens on it, we're actually going to decrease the oxidation strength of the chromium by adding a chloride to it. Okay, that's going to change it. It's going to make it softer and not as oxidative. And therefore, when we have this complex of the pyridinium chlorochromate, it will stop at the aldehyde. So you need to know that PCC oxidizes alcohols to give it to the aldehyde. So an example of that is right here. So the primary alcohol will be converted just to the aldehyde, okay? And it doesn't go any further, okay? So chromic acid, if you want a carboxylic acid or a ketone, PCC, if you want an aldehyde, write that down. Okay, also tertiary alcohols don't oxidize because there's no hydrogen to remove on the carbon that the OH is on. Therefore, it is stable to these conditions.
Excuse me, I have a question.
Yes.
Does that only, for PCC, does that only apply to primary alcohols?
PCC will only convert primary alcohols to aldehydes. Okay. However, it will convert secondary alcohols to ketones. But we typically use it when we want to convert a primary alcohol to an aldehyde, because we can use that less selective chromic acid to oxidize the ketones from the secondaries.
Okay, thank you.
Okay, so that's a lot about oxygen, alcohols, and what we can do with alcohols. Now let's talk about another functional group that we have. And the only difference is, instead of just having that carbon to oxygen to hydrogen bond, we're going to take away that hydrogen and put another carbon bond. And when we do that, the structure is now called an ether. Okay, so it's different structure because it doesn't have that acidic hydrogen, which means it can't hydrogen bond to other things itself, but it does have different physical properties. Okay, now just like before, oxygen is still sp3 hybridized and has those 2 lone pairs that control its shape. That's why it has that bent shape. Okay, and it's trying to be 109 degrees, but those electron pairs are pushing it, are not taking up as much room, and so the methyl groups are bending it out to around 110. So it's approximately, it's trying to get that 109. Okay. Now we do have polarity now because we have this lone pair and lone pair here, and we have polar bonds. We actually have a net dipole on our system, which we'll talk about next. Okay. So ethers do not change the name of the compound. Okay, ethers are always substituents. Okay, just like halogens are always substituents, ethers are always substituents. And so we have to name them differently. What we do is we take the longest chain and we name it for that, or a ring, for example, we'll name it for that. And then we will put whatever alkyl group is on the other side, the smaller one, and call it the alkoxy substituent. And so when we do that, so if you had an ethyl group with the oxygen, you would call that ethoxy for the ethyl and for the oxygen, and then the longest chain. Okay, so let's do something symmetrical here. So either side we can pick first. So we have 2 carbons, so that becomes ethane. Okay, and the 3 other atoms are now a substituent. So we have the oxygen and 2 carbons, so that's ethyl, but we have to oxygen there, so it's ethoxy. Ethoxy, ethane. Okay, or in the case of common names, what you would do is you would say the 2 different alkyl groups you have and say the word ether. So in this case, we have an ethyl group and an ethyl group and an ether, so it's diethyl ether. So let's look at this one right here, and let's do IUPAC first. So we have 1, 2, 3, 4, 5. So we have oh, that's name wrong. We have 1, 2, 3, 4 carbons. Oh, that's named wrong completely. Oh, this should be propyl. And it shouldn't be all. Okay, so we have 1, 2, 3. So that's propyl. That's propane, sorry, right here, because that's the longest chain. Right here, we have a methoxy group, and so that would be methoxy right there on our 2 carbon. And then we have another methyl group also on our 2 carbon. So we have 2 methyl for this group here. We have 2 methoxy for that group there. And propane for propane for the longest chain, which is those 3 groups. Okay, so let's see, 2 methyl, 2 methoxy propane. And then in the case of our ring, because our ring is named for the alcohol here, this is number 1. And this is an ethyl group here, so it'd be ethoxy. So it'd be 2 ethoxy cyclohexol. And there's probably not a common name for that one. Oh yeah, over here, we have the T-butyl as one group, the methyl group is the other group, and then this word ether for our common name. The 2 different groups attached to the oxygen, and then the oxygen counts for the word ether. Okay, so it's really, again, always name it as a substituent. Okay. Now, there are also some cyclic ethers, and these cyclic ethers actually have common names, and we need to know all 3 of these as our common names because we are going to use them extensively. The first one is called ethylene oxide, right here, and it's actually oxocyclopropane because it's 3 things, but the common name is called ethylene oxide. And we'll also know it as an epoxy, okay? So that will also be epoxy, okay? The other common thing is a very common solvent. It's an ether. It's not very reactive, but it's polar, and we call it THF, which is tetrahydrofuran. And the reason we call that is that this compound here with 2 double bonds here is called furan. And by adding 4 hydrogens to those 2 double bonds, you get 2 tetrahydrofuran. And then this last one here is called dioxane. Diox, so it has 2 oxygens and a ring, ane, dioxane, and they just happen to be in the 1, 2, 3, 4 position. 1, 4 dioxane. Okay. So I said before that now we go from ethers, from alcohols. Alcohols had hydrogen bonding. Ethers no longer have that hydrogen bonding, so all they have is that polar, that dipole-dipole interaction. They do not have the hydrogen bonding. So if we look at that bond here, we have a polar bond between carbon and oxygen, and that's because carbon is less electronegative than oxygen. So it's going to give us a polar bond in that direction, and a polar bond in that direction, meaning that this half of the molecule is going to be partially negative, and this over here is going to be partially positive, meaning that we can get that dipole-dipole interaction in between the different functional groups. Okay, so what does that mean to the physical properties though? So the physical properties are not as affected by the, are not as as high as with alcohols because there's no hydrogen bonding. Okay, so it's higher than if it was an alkane because we have polarity and we have a dipole moment, but it's not as high as with a double bond, hydrogen bonding. So if we look at these, they're the same. There's a 100-degree difference here, but remember that the propane is like negative 48. So we do gain something by having this dipole moment or having this polar molecule. If we take that and go up a molecule here, we actually are not very soluble in water, because all we have is that dipole interaction. We don't have hydrogen bonding, so they're very poorly soluble in water. Again, only one hydrogen bonder, so we start losing solubility. Once we go up a little higher, we can see that the alcohol with 1 oxygen per 5 carbons is barely soluble. The alcohol with 2 hydroxides for 4 carbons is very soluble. The ether derivative is barely soluble in water because it has a dipole moment. And then we have the ethylene glycol dimethyl ether, which actually should have a second OH here, a second oxygen. Because it has 2 different positions with dipoles, it actually can dissolve in water. I'm gonna have to fix all that. So, while ethers themselves don't hydrogen bond, they can act as that Lewis space or be a hydrogen bond acceptor. So that's why you can get them slightly in water, is that they can act as a hydrogen bond acceptor for something with an acidic hydrogen. So that means that it's acting as a Lewis base. Okay. So that being said, that significant difference in hydrogen bonding is demonstrated by the lack of the higher boiling points you see for the alcohols. Okay, so one of the things about ethers is because they resemble hydrocarbons in their chemical resistance, they're fairly non-reactive. Okay, so they're not strong, they don't, strong oxidizers don't work with them. Most moderate acids and bases don't react with them. That means that we use them as a solvent for a lot of chemical reactions because they don't react. So we can use them in substitution reactions. We can use them in oxidation reactions. We can use them in other reactions because they do not react. So that's why you see THF is a really, really common solvent in a lot of our systems because it is so chemically inert. Okay. That being said, there is an ether that is very chemically reactive, and that's the epoxide, okay? And the reason this is chemically reactive is the fact that it is a 3-membered ring. It's trying to be 109 degrees, and you're forcing it to be 60. So it wants to spring open and release all that energy from having it being forced from 109 down to 60. So epoxides are the exception to the rule about reactivity, and they react in a special way. Okay, so we call them epoxides, and that's because the most common one is called ethylene oxide. And ethylene oxide is basically made from ethylene and oxygen with a catalyst to give us this strained ring system. Excuse me. So it's like you're adding oxygen across that double bond. Okay, now, we name these different things by how long the chain is. So if we only have 2 carbons in our chain, it's ethylene oxide. If we have 3 carbons in our chain, it's propylene oxide. And if we have 4 carbons, it would be butylene oxide, etc. So what kind of things will make this spring open? Okay. Oh, sorry, another way to make them. Another way to make it is to, instead of using high temperature and oxygen and pressure, we can actually make it in our regular chemistry labs using what we call per-acetic acid, okay, or a per-carboxylic acid. By per, right there, peroxy, meaning we have an extra oxygen, okay? So acetic acid looks like this, right here, but per-acetic acid has an extra oxygen to it. And that extra oxygen wants to go somewhere because this oxygen-oxygen bond is actually a very weak bond. And so what it's trying to do is give away that extra oxygen, and it can do it at fairly low temperatures with an alkene. It'll make exactly that same epoxy compound. And so, yeah, anytime you see a per acid or per acetic acid, think it's going to try to transfer that oxygen. Okay, so now let's talk about epoxies, okay? So ethers, if they're bigger than that three-membered ring, not reactive, nothing happens. However, because that ring is so strained and wants to open up, it'll react with any nucleophile and force it to ring open. So in this case here, we have the electrons from this oxygen here. It can come in from the bottom side here, and these electrons will go away with this oxygen here, and we end up getting a hydroxide adding to that system. Okay. So whenever we have an epoxy in water, we end up with a glycol or a diol, a 1,2 diol. Okay. And notice how the stereochemistry here is different. Because this oxygen is taking up the top of that ring, it had to attack from the bottom. And so when it attacks from the bottom, that's where it's going to add. And so you're always going to have these opposite each other when you open a ring with an epoxy. Now, is it just water? No, it turns out any strong nucleophile can do that. Okay. So in the case of what we learned about nucleophiles, amines have that lone pair. It can act as a nucleophile. Water, in the presence of acid or base, can open it up to give you a glycol. Another nucleophile that can form a nice bond is the thiol right here. So in the case of the amine, you're going to end up with an amino alcohol because amino is the substituent, alcohol's main food chain. In this case, we get a diol right here, a 1,2 diol. In this case, we get a thiol and an alcohol. Or in this case, because the thiol is the substituent, we call it mercapto alcohol. Okay, so that means that these rings will open with any good nucleophile to open up and give us an alcohol and whatever else you attacked it with. So if you attacked it with a chlorine, it will be a chlorine ethanol. If you attacked it with an alkoxide, it would be an ether alcohol. Okay. So we can use this to our advantage to build structures, okay? So for example, in the case of this compound here, if we wanted to build this little segment right here, we could easily do that by having our epoxy and then attacking it with our nitrogen compound like this right here to give us our amino alcohol that we can hook together with other things. So we can use this to our advantage as a building block to add 2 carbons and 2 functional groups very quickly to our system. And it's all because we're ring opening that 3-membered ring, the epoxy. Okay. So that being said, let's go to our last functional group for this lecture here. And I'll talk about this again on, let's see. Yeah, okay. So up to now, we had oxygen with a hydrogen on it as our alcohol, okay? And it had a polar bond and a hydrogen bond, okay? Okay, let's move down the table, go from the first row down to another row here, and let's go to sulfur, okay? It is not as electrophilic as oxygen. So that means the sulfur-hydrogen bond is not as polar. However, that sulfur is still sp3 hybridized, and therefore we have those 2 lone pairs, giving us our bent physical geometry. So this is the sulfur analog to an alcohol, and so we call it a thiol. Okay. When we name these, we call it with the thiol as the parent chain if it's the only functional group. Any other functional group, we have to name it as a prefix or as a substituent. And so when we have it as a substituent, we call it mercapto. Okay. So we have ethane thiol or ethyl mercaptan. Interestingly enough, they use methyl thiol or methyl mercaptan as the smell in natural gas. Natural gas has no smell, so they actually have to put one in so that you can see when you can smell when there's a high enough concentration that it could catch fire. So that being said, we have this hydrogen there and we think, oh, it can hydrogen bond, right? Well, the other thing that we have is these low molecular weight thiols here have what we call stench. The human body is designed, or it is it adapted itself to know that sulfur compounds typically mean poisonous things. And therefore we can smell sulfur compounds at very low concentrations. So, and because we can do it at this very low concentration, one drop is enough to clear out the entire chemistry building. We call this particular chemical property stench. Okay, so again, these are added to natural gas as odorants so that we can smell them before we have a high enough concentration of the natural gas or the hydrocarbon to cause an explosion. And we can smell these in parts per billion. Okay, so we start to smell the threshold for this is at parts per billion. Okay, now, because the bond between sulfur and hydrogen is not very polar, in fact, it's about the same as carbon and hydrogen, they don't hydrogen bond, which means that their boiling points are not the same as they were if they were alcohols. Okay, so a methyl thiol has a much lower boiling point because it does not hydrogen bond, and so our ethyl has a much lower boiling point than the oxygen analog because it doesn't. In addition to that, because it doesn't hydrogen bond, it also is poorly soluble in the water. Okay. Just like alcohols, thiols can react as acids. However, they are more acidic than the alcohols because the anion formed is actually less basic. Okay, so the stronger the acid, the weaker the base. It's actually a weaker base, which actually makes it a stronger acid. Okay, notice this is halfway to acetic acid as far as acidity goes. Okay, so in the case of because of that, well, you can't form a nice stable salt with sodium hydroxide and ethanol because it just kind of stops in the middle. But in the case of thiols, they actually do form almost completely the sulfur salt, the sodium salt here, and give off water. In fact, when I used to work with this in grad school, we also used to always save them and store them as salts so they wouldn't stink up the lab too much. So they form these very nice stable salts because of this. Okay. So thiols have actually one really cool reaction, okay? And this really cool reaction is what we call the disulfide reaction, okay? So in the case of disulfide, you can use any oxidizing agent, including air, so it happens in air, and you can take a thiol and a thiol and remove two hydrogens and create a new sulfur-sulfur bond, okay? So this is used extensively in protein chemistry. In fact, when you straighten or curl the hair, the first part of the reaction is the reduction, where it creates a whole bunch of sulfide thiols on the surface of your hair, and then you put it into whatever configuration you want, straight or curly, and then you actually put an oxidizer in there to recreate the disulfide bonds. So when you do a hair perm where you're getting it straight or longer, you're actually breaking disulfide bonds and then making new disulfide bonds. In proteins, we use this because proteins can fold and hold their position because of disulfide bonds. The other cool thing, I don't know if you have it, no. The other cool thing disulfide's done, it's the reaction that makes rubber tires so durable, okay? Rubber tires are made with alkenes. So you have really long chains with a bunch of different alkenes on them, right? And when you react sulfur with these, they actually create these thiols, and then the thiols bind to form disulfide bonds. The cool thing is disulfide bonds are dynamic. They move back and forth. That's why rubber is so strong and so durable, because it has slowly, these disulfide bonds are being formed and broken over and over again to give us this very high wearing material called the butyl rubber, vulcanized butyl rubber. It's vulcanized because you have sulfur in it. Okay. And that is all I have for chapter 8. Okay. So obviously thiols are not used as much as that in organic chemistry. We do use them a lot in protein chemistry and or industrial chemistry. Okay. Questions on alcohols, ethers, or thiols. Remember, the most important of the ethers is the epoxy. Okay, some of you are here. Okay. Okay, well, what I'll do is I will go ahead and stop recording, and you can hang out and ask questions, and I will post this as soon as I can.